Well, welcome to another integrity recording. And in this recording, we're going to begin a discussion of how to characterize distributions. So this corresponds to the notes I've supplied on descriptive statistics for continuous data. So in this section, we're going to talk about something that we measure, and we measure it on a continuous scale. It could be time, weight, height, anything that you would be measuring on a continuous scale. And I thought I'd go back and start with the quincunx again. So remember last time when we introduced variation, we used the quincunx. So we have a funnel centered at 16, and we have a pattern of pins that act as sources of common cause variation. So if we begin to drop beads, what happens? The pattern starts to emerge. In other words, the collective action of all those pins causing each bead to bounce around results in getting a distribution of positions, okay, for the beads. Well, I'm going to take off the animation, and remember, I'll just reset this, and we'll drop a lot of beads. If we take enough observations, in this case we're observing the positions of the beads that go through the pins, we see that a distribution shows up. What is a distribution? It's just a collective pattern of variation over lots of observations. So when we watch a distribution develop, it tells us a lot about how the variable varies. Okay. So in our case, I'm dropping a lot of beads, and we're seeing that the distribution is somewhat mound-shaped, and it's centered at around 16, as you would expect. Okay. So what we're going to do in this section is talk about, well, what are the ways we can actually describe this variation? In other words, in a Six Sigma project, our goal is to reduce the variation, but in order to do that, we first need a way to characterize it. How would we explain to someone else, or even to ourselves, exactly how does this random variable vary? So our goal in this section will be starting to develop some tools to describe the variation. So at this point, I'm going to switch back to the slides, but I think the quincunx gives you a good idea of what is meant by a variation. By observing the random variable over some period of time, we collect a lot of observations, and the distribution reflects the pattern of variation that we have seen. Okay. So, as I said, these are the notes on descriptive statistics for continuous distributions, and I'm going to, and I might actually go ahead and open the JMP software, and we might begin to start making some use of it. Taking it a moment to start up. There we go. So what we'll do is I'll go to the correct directory. And I'll open a couple of files that we're going to actually use just to speed things up a little bit. Okay, so let me go on to slideshow. And I'm going to begin by just a quick reminder that how you actually describe data or analyze it is to a large part determined by the kind of data you're collecting. So I have discussed this, but I want to review it. So there are basically three types of data. One is called nominal. Some people call it categorical. And this is a random variable where what you actually observe are just categories. An example of a nominal variable is colors of M&Ms. So you open a bag and you observe the colors of the M&Ms and you tally how many show up in the bag for each color. So since our variable is color and its levels are just whatever the different colors are, we call it a nominal variable. Now, if you inspect, say, parts and they either pass or fail, that's nominal data. They're on one category or the other. Another type of data is called ordinal. And these are also categories, but ordinal categories have an ordering to them. And you've all seen this type of data before. A simple example is a typical survey like you might do in a restaurant, and they ask you to rate the service from, let's say, 1 terrible to 5 really good. So categories are 1, 2, 3, 4, 5, and each category is considered a better ranking. So even though those numbers are really categories, not measurements, they have an order to them, so we call it ordinal data. This is the type of data we'll spend the least time on this semester, and probably the one we'll spend the most time on is continuous data. Continuous measurements, again, are anything you measure on a continuous scale. Okay. And I should point out, and you'll see this, it's important in JUMP to make sure the variables are defined correctly, because how JUMP lets you analyze the data depends on the type. In other words, as I mentioned, the type of data largely determines the different things you can do to analyze that data. Okay. And by the way, if you work in the field of quality, nominal data is often called attribute data, attributes of a part, and continuous data is often called variables data. They actually don't have a separate term for ordinal. So people who work in quality occasionally will hear the term attribute or attribute data. It means the same thing as nominal or categorical. So here's a simple example. This is a study being done on delivery times. In other words, how long is it taking to deliver a product to a customer? Okay, so this is the number of days it's taken from when an order is placed until the order has been shipped. Okay, so notice in JUMP, in fact, let me open up a pen. Notice in JUMP, in the columns window, there's always an icon, and that tells you the kind of data. So the blue triangle means it's continuous data. That's the icon for it. And it is a continuous scale. Okay, we're measuring it only in days, but we could even measure it to microseconds. But obviously for this data, it wouldn't make a lot of sense. And if you look in the rows menu, you can see that there are 100 observations. Okay. One of the ways to show data is a stem and leaf plot. I'll let you read about them. You can do them in JUMP. I don't really use them much myself, but some people like them, so I just include a slide about them. Again, in the what's called the distribution platform of JUMP, they create what are called stem and leaf plots, but we're going to focus on what are called histograms, which happens to be a really old way of visualizing a distribution. So on slide 8 is a histogram of delivery times. And how you make the histogram is, well, the scale runs from 0 to 50 days. So you break it up into some convenient bins. So here they're broken up, you'll notice, into 5-day bins. And then you count how many observations fell in each bin. So notice for 0 to 5 days, about 35 orders fell in that range. and for 5 to 10 days, maybe about 27, and so forth. Okay. So what we can see from this distribution that a high percentage of our orders are shipped within actually 15 days, but it can take as long as 50 days to get an order shipped. So part of a Six Sigma program would be to dig into this data and try to figure out what on earth causes so much variation in time to delivery. And this is important because many organizations, not just companies, discover the longer it takes you to deliver a product or service, the more likely you are to lose the potential client or customer. Okay. And in JUMP, when we analyze distributions, no surprise, it's called a distribution platform. So let me go over to JUMP, and I see I wanted the delivery times data. So here's the delivery times data in JUMP. So I want to look at its distribution. I want to examine the distribution of delivery times. So I would go to the Analyze menu, and the first option is Distribution. And these are platforms. What JUMP means by a platform, it's a collection of statistical analyses that could be applied to the same type of data. So they just put them into one platform that makes it much easier to use in the software and analyze. And so I only have one column I want to look at, delivery times. So I put that in the columns box. Click OK. By the way, sometimes we call this the launch window or the launch dialog for each platform. And you'll see many of them as we go further into JUMP during the semester. Okay. So notice, and I'm going to get rid of something called a box plot. We don't need that right now. Okay. Remember, when you have a JUMP graphic and you want to resize it, you can do it dynamically. Put the cursor in the lower right-hand corner and drag and drop. Okay, so here is our histogram, and we have let JUMP choose the number of bins. JUMP, usually we just let the software figure out how many bins to select. So JUMP said bins of width 5 were about right. So, and by the way, if you want to know how many bins, a small rule of thumb cancel is roughly the square root of the sample size until you get up to a few hundred observations. So about 10 bins. So 10 bins of size 5 works well. And also, again, in any JUMP graphic, put the cursor in the middle, right click, and up comes a menu of further use. So maybe I want to change the color. I'm not going to do much with this. Okay. And so we changed it to dark blue. Okay. Also, keep in mind, and we're going to make use of this later on, that the histogram, okay, let's see, is always tied to the spreadsheet. Okay. So if I click on a bar, let's click on 0 to 5. Okay. So I'm clicking on 0 to 5. Let me get this out of the way. And what that shows me is I've selected 36 observations. So notice in the row state area, 36 of them are highlighted. If I double clicked on this bar, it would create a new data table only containing deliveries that are up to 5 days. Maybe you're only interested in deliveries in that range. So you could create a data table and just focus all your efforts on those values. Basically, we refer to this as filtering the data. In other words, filtering out the observations that you actually want. Okay. So notice again the distribution, and you'll see in a moment, we call this right skewed. It has a long right tail. And there are lots of options for histograms. Notice the down arrow for delivery times. We click on it. Histogram options. And we can do things such as show percents. So this shows what percent of the observations fell in each bin. Okay, so as we said, 36 of them were 0 to 5, 27% 5 to 10, and 18% 10 to 15. So you can see about actually, let's see, 18, 27, that would be 45, 36, about 80% of the observations fall in that range. Okay, so basically what we're doing, we're starting to describe the distribution of the data. And again, a quick reminder, you should have watched those JUMP introductory videos, the YouTube videos. Remember, any place in JUMP where you see this down arrow, there are all kinds of additional options. Okay, so we won't use all of them, but during the semester, as we analyze our data, particularly in the analyze phase, we'll make a lot of use of some of these options. Okay. So I'm going to skip through the next few slides because this is just showing you what I just did. And again, we call this a right skewed distribution. Skewed means the direction of the long tail. So it's to the right, so we call it right skewed. What else could we say about the distribution? Well, I just said the shape is right skewed. Well, something else we'd be interested in is where is the distribution actually centered? Well, it looks like it's centered somewhere close to 5 days. That's really where the peak occurs. And how much spread? Well, take a look. We get variation from 5 to 10 days. So I looked at 3 things. Where's it centered? What's the spread? And what's the shape? Those are 3 things that you can get out of looking at a histogram that tells you about the distribution. Okay. So now we can begin to tell people, well, it's a right skewed distribution. Variation is running from around 0 to 50 days. Okay. And our typical delivery time is in the range of 5 days. So without computing any statistics, you've already basically started to describe the behavior of delivery times, the variation that occurs in delivery times. Well, here's another data set, and I'll use this off and on, and this is more of an engineering example. In this particular case, they have a material called aluminum lithium. It's an alloy used in aerospace. It's relatively strong, and because they use lithium as an alloying element, it's fairly light. So you can see why aerospace applications, they like it. So this is an engineering study to study the strength of the material. So they have 80 samples, they take them in the lab and they break them. And the breaking stress, you don't have to worry about this, is measured in engineering units of kilo-inch pounds per square inch. That stands for basically the same idea as pounds per square inch, except that it's in units of 1,000. Okay. So basically, it's a measure of how much force was required to break the coupon. Okay. So a designer for an airframe would want to know, well, how much stress can this particular component withstand? And this is part of trying to answer that question. So again, we go to the distribution platform, click on KSI, put it as, it's the only column we want to look at right now. And notice this distribution. So again, I'll just kind of click over to jump. Okay. We'll look at the aluminum lithium data. Okay. So I go to the Analyze menu, select Distribution, and I only want to look at KSI. That's all I'm really interested in. Okay. There we go. And again, the thing you see above the histogram, I'm having a little trouble with my mouse right now. There we go. So I'm going to expand the histogram a little bit. And I'm going to get rid of what's called an outlier box plot. We'll talk about those later on. Okay. So also in JMP, in the different report windows, at the very top is this blue ribbon. And what that is, that's a hidden menu. Again, the goal of JMP is to keep the real estate on the screen as uncluttered as possible. So they tend to hide a lot of options in these various menus. Once you know where they are, it's pretty darn easy to click on them and then select whatever option you want. Well, here is a cursor toolbar, and they have a number of neat tools we use off and on. One of them is called the grabber or hand tool. Okay, and for fans of the Addams family, I like to call it the thing tool. Okay, you'll have to figure that out. So I grab the tool, I bring it down. Notice by default, JMP has picked 1, 2, 3, 4, 5, 6, 7 bins, and each bin is about 25 KSI wide. And as we showed before, basically what you do is you count how many observations fall in each bin, and then you plot the frequency. Okay? You can plot the frequencies or the counts. It really doesn't matter, whichever way you want to do it. So I'll use a count axis. Okay. So the height of the bar is just how many observations occurred in that bin. Okay. Well, what if I want to change the bin sizes? In other words, I've decided I don't want 7, I want 10. Well, you put the hand tool in the histogram display, and you move it up and down. Okay. And I think you can see just looking at it, here I've got, a lot of bars. Each one appears to be 1 or 2 units wide. So that's not very useful for describing the distribution. Okay. So I bring the tool down, we're getting wider and wider bins. So here's where JMP used as a default 7. It appears to be a good number. Notice it gives us a clear picture of the distribution. And if I keep going, now clearly my bins are too wide and I really have little or no information. The question always comes up about how many bins to use. Honestly, using statistical software, for the most part, just use the defaults. There are all kinds of algorithms that people have created over the years, or even textbooks that were written on histograms. But generally, these days, people use software and they have algorithms built into them. Again, a simple rule is roughly the square root of the sample size until you get up to, say, like a few hundred observations. And then you have to use other rules, because if I had 10,000 observations, the square root of the sample size, we'd end up with an enormous number of bins. So again, I don't want to complicate this. I think you'll find in general, just going with the defaults works fine. Okay. So this is the histogram. Notice this one is centered somewhere around 160. Okay. It's symmetric. This one, both tails are about the same size. So I would call this a mound-shaped symmetric distribution. I'd say it's centered about 160, and the spread roughly runs from about 75 to 250. So again, you've described the variation or the random behavior of the strength. By the way, this would bother a designer. It's running from 75 KSI to almost 250, and it's centered about 160. Okay. So yes, I'd say it's a mound-shaped, it's symmetric, and centered around 160 and runs from about 75 to 250, which is actually for this application, that's an excessive amount of variation. So in general, we'd have to do some work to tighten up the distribution. Okay, so I'm going to go back to slideshow. And notice in slideshow, we talk about the basic types of distributions, basically symmetric and left skewed or right skewed are basically the most common that you'll encounter. Okay. Other shapes can occur. By the way, if you see more than one peak area, notice this one on slide 17, if you look at it carefully, there are two peaks. We would call this one bimodal or multimodal. I'll show you an example later. What this actually indicates is you've gotten two different distributions mixed together. For instance, you may have mixed together, if we're studying heights of human beings, you may have accidentally mixed adults and children together, and then you discover two distributions, and what you'd have to do is dig into the data and figure out what's causing that. And generally, you're going to find most of the time there's a single peak or unimodal, meaning one distribution. And sometimes there really isn't a peak area. We won't run into this very often, if at all, this semester. And we call that uniform, but it's not common. It can occur, but not very common. Okay. And I mentioned we also want to measure the spread. So here we have three distributions, all centered at 20, all symmetric and mound-shaped, but notice where they differ. Look at the level of variation in the three distributions. So in describing the distributions, I'd say they're symmetric and mound-shaped. They're centered around 20, but each one of them has a different level of variation. We see more spread, meaning there's more variation, with distribution C being much more variable than the other two. Okay, so histograms, again, it's a very old way of displaying visually a distribution for a continuous random variable. It does allow us to look at where it's centered. In other words, overall, where is the distribution centered? Where do the observations tend to cluster? How much spread is there and what's the shape? Something to be careful of with histograms, typically before you want to make any firm statements about the shape of the distribution, you really need 75 to 100 observations. Maybe 50, but say 75 to 100. With smaller sample sizes, the histograms are unstable, and if you make small changes in the widths of the bins, the shapes can change dramatically. So there's not an exact rule, but I would say a minimum of 50, preferably 75 to 100 on up. Okay. So improper bin sizing is one of the problems that sometimes occurs. And I'm just showing you an example, and I did it visually in JUMP. You can see a histogram with 9 bins of width 20. And that gives you a good look at the shape of the distribution. 18 bins seems to be too many. And notice we're getting a lot more noise in the distribution. And then 5 bins really are too small. Okay. In other words, basically this is based on 80 observations, and 9 turned out to be the square root of 80, about right. Okay, so I'm going to stop at this point, and then we're going to talk about what happens to distributions over time.